All right, everybody. So in this video, we are going to have our last part of Unit 4, which is about heating and cooling curves. So a heating and cooling curve depicts the, specifically a heating curve depicts the endothermic process, okay, because it's heating up, where the heat is being transferred from the environment or the surroundings into the system. On the other hand, a cooling curve depicts the exothermic process where the heat is being transferred from the system to the surroundings or the environment. So a cooling curve is cooling down because it is releasing heat, whereas a heating curve is heating up because whatever your thing is, it's absorbing the heat, which causes the overall temperature to rise. Now, during the actual phase change, energy that is being transferred to or from the molecules is being used to change the state of matter or the phase of matter. Not the temperature, okay? So at those flat lines, okay, where the phase changes occur, the temperature doesn't change because the energy can only be used to change one thing at a time. It's either changing the temperature or it's changing the phase. And it changes the phase by breaking or forming the intermolecular forces, which are called IMFs, and those are between the molecules. So for example, if I have a water molecule that looks like this, and I have another neighboring water molecule, they're all in a glass or something like that, there is an intermolecular force that kind of bonds and attracts them together. It's not a full bond, it's just like a force, like a magnet, and it keeps them together. So the stronger they are, the harder it is to change them. So if we look at a heating curve specifically, we want to label for each of these graphs whether it's endo or exothermic, how the energy is changing the molecules, and the name of the process happening at each of these spots. So this is an endothermic process. We know because the temperature from where you start, let's say this is 0 degrees Celsius, compared to where you end, let's say that's 120 degrees Celsius, it increases. So that means it absorbed heat. Now, actually, let's say this is like negative 20 degrees Celsius, because what happens at 0 degrees Celsius for water, G and F represent the melting and boiling points of water. So when water is below 0 degrees, anywhere from 0 to negative 20, this is where you have a solid. And so what happens is as you go, the temperature starts to rise. The molecules start moving faster and faster and faster because changing the temperature changes the speed. So at point A, the molecules start speeding up. So the molecules speed up. Now, as soon as it gets to 0 degrees right here, this process, for that entire time, the temperature doesn't change. And that's because instead of the molecules speeding up, which is what the temperature measures, the speed stays the same and the energy is used to break the intermolecular forces. So what you have here is your solid starts to melt. So here we have the process of melting. And so this means at this point that your intermolecular forces, or IMFs, which I'm going to use from now on after I write it this one time, your intermolecular forces are starting to weaken. And that's what allows the molecules to kind of spread out and give that melting look. in a liquid, because in a solid it's all tight and held together, but for a liquid it kind of separates. Now they're still connected, there are still those IMFs there, but they are weaker, so it allows the molecules to spread out. And then once it's all completely done, well, then it's all a liquid. And so that liquid starts to heat up. So right here at point C, we have all liquid. And just like when in part A, the molecules are speeding up. And then when we get to point D at 100 degrees Celsius, well, we see that there's another phase change happening. And this is going to be the change between a liquid and a gas. So this is vaporization. Now there are two processes in vaporization, and this is boiling and evaporation. Now at this point here, in order for these molecules to change into a gas, which is what we have in segment E, this means that the IMFs, or the intermolecular forces, completely break. And that's what allows the molecules to separate completely and just travel all around the room as a gas, as steam. So in the flat sections, it's all about the intermolecular forces. And for the diagonal sections, it's all about how the molecules are speeding up. So the angled areas, these angled areas in green, speeding up. Flat sections, your IMFs are weakening or breaking. Now, if we look at a cooling curve, what's interesting is that melting and freezing and vaporization and boiling, those phase changes, they actually happen at the same temperature. It just depends on whether or not you're adding heat to break them, or if you're removing the heat or releasing the heat in order to strengthen those intermolecular forces. So if, at the beginning of the time, we start up here, okay, so in this part, section A, we're starting as a gas. And what happens here is that the gas molecules from left to right, the temperature's going down. And that tells us that right here, the molecules are beginning to slow down. Okay, so in a heating curve, the molecules speed up, and in a cooling curve, they slow down. Now, when the gas reaches at about 100 degrees, it will begin to condense. So this is where we see condensation happen. And this is what happens on your glass. If you have a really cold, like glass of water or a water bottle, and you start to get that liquid on the outside, that is water that was once in the gas form in the air, and it's now a liquid on the side of your cup. And then once it's all a liquid, the liquid can begin to cool down even further. So here in segment C, we have a liquid. And again, the molecules are slowing down when the temperature is cooling down. And then again, we have another flat section, which means we have another phase change. Now we know that when a liquid gets cold enough, in this case at 0 degrees Celsius, it will start to freeze. Now at these phase changes, okay, so for condensation, we know that these intermolecular forces begin to form. So there are no intermolecular forces in gases, and there are in liquids. So condensation kind of creates them, which is why they come together and create those little beads of water on the side of your cup. But when you freeze, the intermolecular forces are already there, but they are just being strengthened and made stronger, which pulls the liquid tight into segment E, which is a solid, and as it begins to be more solid and it releases more heat, the temperature decreases and your molecules slow down. So the moral of the story, the slanted lines where the temperature is changing, that means the speed of your molecules is either speeding up or slowing down. And then the phase changes, or the flat sections that I highlighted in purple, that is where your intermolecular forces are changing. And so for that, we did A, B, and C kind of just all on the graph there. So hopefully that makes sense. And in our next video, we will look at unit number 5.